Hi, welcome back. This is the review video for the first test in Calc 2, and I'll begin by kind of giving you a heads-up question pool. So you can expect questions similar to these type of problems that you would find in the WebAssign section. So from 8.1, questions 1 to 12, and then I'll pick about 4 of those for the test. So 4Q means 4 questions on the test. Next section is 6.2. And from there, I'll pick problems like 1 to 9. And again, I'm going to pick about 4 of those. 7.1, questions 1 to 12. And from there, I'm just going to take about 2 of them. 7.2, questions like 1 to 6. And then 8 to 10. And I'll pick 2 of those. And these will be Y or X-axis rotations only. So if you remember, there's shifted axis rotations. I'm not going to include those on the test. 7.3, we had the shell methods, so problems like 1 to 7. And again, I'll take about 2 questions from those. 2Q, 2Q, 2Q. And then finally 7.4, questions like 1 to 7. And again, I'll be taking 2 of those. Okay. So in this video, I want to go over the pretest and kind of remind you of the formulas that you'll be needing to successfully navigate the exam. So you can go to Blackboard and open up the pretest. So I recommend that you do the pretest first and then kind of watch this video afterwards to see what you did wrong. There's no video quiz question in this video, so it's kind of up to you to watch if you need to watch. So 1620 for the pretests, I put those in the course content tab, and there you see our first pretest, and it's downloading. I want to open up. It's in Microsoft Word, so that you can open that up. If not, send me an email and I'll send it out to you. Okay, so the first set of problems are just integral problems from Calc 1. So there's, you have to have your basic formulas memorized, like the power rule. So the most important rule that we learn is the power rule formula. But I went through the most important ones there in class. You should have them all memorized. It's basically your fundamental vocabulary of calculus. And just like in foreign languages, you're going to need those things memorized to be fluent. Okay. So of course you could always use some sort of translator, but we want a level of fluency so we can talk back and forth about things without having to constantly look things up or worry about translation error. Okay, so have those guys memorized. So it'll be the basic formulas plus some U substitutions. So for 8.1, you need basic formulas. And I gave you those lists in class, and it's in our class notes there as well. And then you need to have U sub. So first, basic formulas. That's just one example of one of the formulas. And then 2, you should be able to do U subs. And then 3, we should know how to do basic algebraic transformations, such as completing the square and what is long division, or if you like to do synthetic division, you could do that as well. Okay, so you should be able to do any of those types of transformations and any of the stuff you would need to perform questions like 1 to 12 in WebAssign. Okay, every once in a while I will take problems from the homework though as well. So if you're really kind of compulsive about doing if you want to become a teacher someday, a calc teacher or something like that, you may want to go into 8.1 and maybe chug through some of the exercises on top of the WebAssign. Because in WebAssign, I mean, it's a summer class, so we don't really have tons of time, but ideally you would be kind of going back to chapter 8 and chugging through some of the the exercises, right? So just looking at these, and the stupid thing isn't downloading correctly. But hopefully you understand what I mean. So anyways, let's take a look at problem 1 here on my pretest. I have the integral of 17 all over x minus 13 to the 17th power dx. Okay, so you definitely do not want to, FOIL out that denominator, multiply it 17 times by itself. That's insane. So what you'll do is some sort of u sub to make it a simpler integral. And usually the good rule of thumb is just to let u equal whatever's in parentheses. Okay, and then we have our differential. The derivative of x is 1, and then the derivative of 13 is 0. So you just have 1 dx. In other words, you could replace dx with du. Okay. All right, you can factor that 17 out of the integral. Any factor that is not dependent on x, you can move it out of the integral. Then you'll have 1 all over u to the 17th times dx, which is now du. So the two substitutions I generally will do will be this guy and then this last guy. But of course that doesn't always work, and sometimes you have to go back and play around a bit, but for the most part it'll get the job done. Okay, in order to integrate that fraction, I need to rewrite it so I can apply the power rule. So I rewrite it with a negative exponent, and then it's going to be u to the negative 17 plus 1 is negative 16. Divide by that new exponent, and you get that expression. And then we want to back sub and hopefully clean it up. Okay, so factoring out the negative 16, we get negative 17 over 16. And then back subbing the u, it's x minus 13 to the negative 16. And we generally frown upon negative exponents. I mean, this answer here is fine, but in general, math teachers will probably want you to pull that x minus 13 to the denominator. Okay, I wouldn't take off if you did, like, this answer is fine, this answer is fine. I don't have an issue with either one, but okay, great. Number 2, we see one of the basic algebraic transformations we could do to the integrand, and that would be long division, or you could do, in this case, synthetic division, but long division is safer because if there's a coefficient in front of that x, you're either going to have to factor it out or you're going to have to do long division. Synthetic division doesn't work if there's a factor in front of x. Okay, so in my opinion, doing long division is kind of a surefire method. Synthetic is just quicker, and it depends on the kind of work you're doing, whether you want to use long or synthetic. But I refuse to set up my division symbol correctly. I apologize, but it's x minus 6 dividing into x squared. And so what times x is x squared? Well, x. And then you multiply x times x minus 6. So you get x squared minus 6x. Then we need to subtract. So you subtract the entire binomial. X squared minus x squared is 0. And then 0x minus negative 6x is positive 6x. And then we could say, what times x is 6x? Well, that will be plus 6. So I'll have 6x and then minus 36 when I do my distribution. Again, subtract. 6x minus 6x is 0. 0 minus minus 36 is positive 36. And that will allow us to rewrite our integrand. So when you do your rewrite, it'll be x plus 6 plus 36 all over x minus 6. So it's this clockwise rotation in order to do your rewrite. Again, it's x plus 6 plus the fraction 36 all over x minus 6. Okay, that will be all that jazz inside your integral. Okay, so once that's set up, we can integrate term by term. So we'll have x squared over 2 plus 6x plus this last integral. You can factor out the 36. And that's just going to be an ln of x minus 6. You want to be a little careful, though, when you're dealing with this. It really is a u sub. And sometimes you'll lose a factor if you're not going to be careful. But doing the u sub, which I don't, you don't have to do the u sub for simple problems like this. It'll be 1 all over u du. And then, of course, this will be x squared over 2 plus 6x plus 36 ln absolute value of u. Let's see, and then back sub. But I should be seeing work, you know, and your work should look similar to mine. If not, I'm going to wonder if you're using a calculator of some sort, or if you found some clever way to cheat on me. Okay. So you should be showing work. It should be consistent with what we do in class and what we do in the book. Okay. Number 3 is complete the square. So another type of algebraic transformation we do. Integral 35 all over the square root of 4x minus x squared. So if you tried to pull a u sub on the 4x minus x squared, you couldn't get that nice cancellations. So it's not of that type of form, and the form it is an arc sine. So the arc sine formula, if you remember, is the formula 1 over the square root of a squared, which is constant, minus u squared du, and the formula will say that's equal to sine inverse of u all over a plus c. So we need to transfer or do a transformation of the integrand into that form, and we could do that by completing the square. We can also factor out the 35 because it's not dependent on x. Then I have the square root of, and to complete the square I need a positive coefficient of 1 on the leading term. So I factor out the negative, I have minus 4x. And then the thing you add in is b all over 2 squared. So the b value here is negative 4. So in our case, this will equal negative 4 all over 2 squared, which will be 4. Okay, so you immediately add that in, and then to even it out, you're adding it again. You technically have subtracted it in because of this negative on the outside. You've not really added in 4, you've subtracted 4. Okay, so to even it out, to make things work, you need to now add 4 in. Okay, so hopefully that's clear. At this point, you can rewrite. So this will be the 35 integral of 1 all over the square root of 4 minus this x squared minus 4x plus 4, but you want to factor it into a binomial. So this will be x minus 2 squared and then dx. Okay, now it's almost in the form. We want to replace this x minus 2 with just a u expression. U for the x minus 2, du will just be dx. So don't have to worry about any constants or anything. So we have a 35 integral 1 all over the square root of 4 minus u squared times dx, which is du. And then that will be 35 arc sine of u all over the a value is 2, not 4. And then plus c, and finally back subbing. We get that as our final answer. Okay, one more from that section. Let's look at number 4. So I took all these problems, I just took them straight from WebAssign, and I'll probably do that on the test, but like I said, sometimes I'll take one from the homework exercises just to keep people on their toes. Okay. Anyway, 0 to the 12. Then we have 2x all over the square root of x squared plus 25 dx. And here, you're going to have to do a u sub on the denominator. So inside the radical, I have the x squared plus 25. Du will be the derivative of x squared is 2x dx. The 25, the derivative is 25, 0. So dx will just be du over 2x. When you do u subs and you have a definite integral, which is an integral that equals a number once you're done, you drop the limits or you change the limits. I am of the, I prefer to just drop the limits and then back sub everything at the end, okay? You could do it the other way, that's fine, if that's the way you like it. Okay, but this is the way I do it. So 2x over square root of u, or u to the 1/2, times dx, which is now du over 2x. And you require a cancellation amongst the x's, and we have that. It's a real nice cancellation. In order to integrate, I'm going to have to rewrite 1 over u to the 1/2 as u to the negative 1/2 du. And then I can go ahead and use power rule. Negative 1/2 plus 1 is positive 1/2. And then divided by 1/2 is the same as multiplying by the reciprocal 2. Remind yourself to evaluate. And then finally back sub. Um, 12 squared is 144 plus 25 is 169, I believe. And then plug in 0, so 0 plus 25 is 25. So it'll be 2 times 13 minus 5, which is 2 times 8, which is 16. Okay. So I'll pick 4 integral problems, and then the next section was some basics of differential equations. It was 6.2. And the only formula you really need in this section would have been y equals c e to the kt. So you'll have to have that memorized. Other than that, it's separation of variable problems on my test. So for instance, number 5, we have dy over dx equals 28 minus y. So the deal is to get all the y stuff on one side, all the x stuff on the other, using multiplication and division. So I'm going to divide both sides by the 28 minus y and multiply both sides by dx. And then once you get it separated, you integrate on both sides. Okay, so integrate, integrate. On the left side, you'll need a u sub. Okay. So on the left side, I'll have the integral. Instead of dy, you put negative du all over u. On the right side, you can go ahead and integrate that. The integral of 1 dx is just x. And then we store our constant of integration on the right. Integrate on the left, you'll get negative ln absolute value of u. And this, we need the back sub. Okay, so negative ln absolute value 28 minus y. Okay, this is an implicit solution, but we want the explicit solution. We want y equals something, if possible. It's not always possible, but here it is. And to do that, you're going to exponentiate on both sides. So you want to be a little bit careful with that negative. If we exponentiate right here, there's going to be a lot more work. So what we need to do is get this negative on the other side. Okay? It'll make life a lot easier. So multiplying both sides by a negative, you get ln absolute value 28 minus y equals negative x. And then that plus, you think, well, it has to be minus c, right? No. Plus c. The constant c will absorb that negative. Remember, this plus c is just kind of a movement generator. It moves the form of the curve, the kind of primary curve, up and down in the plane, creating a family of curves. And I talked about that in our video. Okay. Once you're here, though, you can exponentiate on both sides. On the left, you'll just have absolute value 28 minus y. On the right, I'll go ahead and split that up using rules of exponents. And then drop your absolute values, replace with plus or minus, reorder. I'm going to rewrite this plus minus e to the c as just a big constant. That thing will absorb any other constants. Notice it doesn't absorb the e to the negative x. So that thing is variable, and it won't absorb variables. Anyways, now we want to solve for y. So if I add y to the other side and subtract the c on both sides, yeah, technically you'll have minus c e to the negative x, but again, that constant will absorb the negative, okay? And then on the other side you have y, or if you'd rather, y equals c e to the negative x plus 28. Just flip-flopping sides and then commutative law of addition to reorder, okay? Okay, let's look at number 6. Number 6 and 7, they're still playing the separation of variables game. Okay? So it's a very special technique important technique for differential equations. Of course, you take the main class, you'll learn all of the different techniques for simple sort of differential equations. So anyways, here we have dy over dx, just rewriting y prime. and then 20x to the 1/2 y. Move everything around, so you get dy over y equals 20. Leave the constants on the right-hand side. Okay, that's a good rule of thumb to have as you do this type of work. Integrate both sides, ln absolute value of y. On the right-hand side, I have factor out the 20. Power rule on x to the 1/2 gives me x to the 3/2 times 2/3. And then that's where your constant is. Now we can exponentiate on both sides. Absolute value of y is e to the 40/3 x to the 3/2 times e to the c. And then we could drop the absolute values, replace the plus or minus e to the c with a big constant, and you get y equals c e to the 40/3 x to the 3/2. Okay. Let's look at number 7. Let's get xy plus y prime equals 48x. Same problem, it's just now it's mixed up a little bit. It's more jumbled. And so your first step is to get the dy over dx on one side and everything else on the other. So to pull that off, you just subtract xy to both sides. So I'm going to have 48x minus xy. And then we can factor the right-hand side by pulling out a common factor of x. So I get 48 minus y. And now we could separate dy over 48 minus y equals x dx. Okay. So now integrate both sides, doing a u sub on the left. Du is going to be negative dy, so dy can be replaced by negative du. So on the left side, we have the integral negative du over u. On the right side, x squared over 2 plus c. Then this will be negative ln absolute value of u. X squared over 2 plus c. Back sub, again, you want to get that negative on the right. So you got the ln absolute value 48 minus y equals negative x squared over 2. Technically minus c, but the constant absorbs all the negative stuff. And then we can exponentiate. And then drop the absolute values, replace with plus or minus, and then replace the plus minus e to the c with c. And then finally solve for y. So we'll just add the y and then subtract the c to the negative x squared over 2. Flip-flop sides, you get y equals ce to the negative x squared over 2 plus 48. Okay, so some good separation of variable problems. That's how we generate the formula for exponential growth. So remember, the basic formula is that the rate of change of the population y with respect to time is proportional to the population. And if you use the strategy above with the separation of variables, you'll end up with the formula y equals ce to the kt, which we need memorized for the test. Okay, so why do I need it memorized? Because I'm going to throw one of these complete the table problems on there. So for example, number 8, we're given that the half-life is 1599 for this radon. And then we're also given the amount after 1,000 years. So we begin just by writing our template formula. We need to solve for C and K. So use the half-life first. So the half-life means that half the initial amount, and the initial amount is C, will be left over after this 1,599 years. So you just plug T equals 1599. So you could write it out if you wanted. T is going to be 1599, and then you're going to replace Y with 1/2 times the initial amount. Okay, so if you do that, you can solve for K. Dividing both sides by C, you'll just get 1/2. And then ln on both sides. Divide by 1599. Okay, and that allows you to rewrite then your formula as y equals ce to the k. Let's put the t in front. So t ln 1/2 divided by 1599. Okay. So we got the k value. Now we need the c value. So use the third column there. The amount after 1,000 years is 1.5. So in that case, that's telling you that you want to replace t with 1,000 and then y with 1.5. Okay. So it's 1.5 equals ce to the 1,000 ln of 1/2 all over 1599, and then just solve for c. So solve for c by dividing. You can't simplify this expression. I've seen some people try that in homework. It won't work. It is what it is, okay? And I say round your answer to 2 decimals, so we'll take that critter and rewrite it. So we have, what is it, 1.5 divided by, I'm just doing this in my calculator real quick, e to the 1,000 times ln of 1/2 divided by 1599. Hopefully that'll work. 2.31 to 2 decimals. So the thing that goes into the third column, that space in the third column, the initial value is 2.31. Then we could write our equation officially as 2.31 e to the t ln of 1/2 over 1599, and use that to solve out for any other unknowns. So the only other unknown is this last column. What is y when t is about 10,000? And that's just really plug and chug. Right? So you dump that into your calculator and see what you get. Let me do that real quick. If you can find the button. There you are. Getting 0.03 grams. Okay, so yeah, there'll definitely be a chart problem. Probably one of the radioactive decay problems. I don't think I'll do the doubling time. Okay, so after that, then that was 6.1. Then we get into 7.1, and the formula there that you need to have kind of remembered is basically top curve minus bottom curve, right? So you're finding the area between two curves. So it's top minus bottom, or in the horizontal orientation, or right minus left. But that's really top minus bottom again, right? If you think about the Riemann person. Okay. Notice nothing's squared here, so this isn't a matter of pi r squared like with the rotation problem. So if I see a pi in there, I'm going to get ticked off. So don't be that person. Anyways, let's look at number 9. Again, what we're trying to do is get the area between the curves. I need you to sketch the region first. So you should be able to sketch basic things like this stuff. Y equals x squared is a parabola with a vertex at 0, 0. Y equals 2 minus x has a y-intercept at 2 and a slope down 1 over 1. So it's a line with negative slope like that. We want the area between these two curves. So far we kind of, it's 2 minus x and then minus the bottom curve. So the Riemann person is in this orientation running across. The rectangles are vertically oriented. Top is the linear curve, 2 minus x, and the bottom is the x squared. Okay, great. Now we need to tell the Riemann person from where to where, right? So I need to set these two equations equal to each other to get the intersection points. I'll have x squared plus x minus 2 factor. So x is negative 2 and 1. And then integrate. And then evaluate the antiderivative. 8 minus 9/3, which is 3, minus 1/2, which is 9/2. Okay. Okay, great. Next, so the next problem we have kind of the other orientation where Riemann person is going up the flagpole, and the big red flag there is you're in terms of y. Okay, so you'd want to do this. We saw in the video that if you kind of try the other orientation, you end up with having to do like a square root function. You have a plus or minus, so you really have two integrals you need to evaluate. But if you shift the orientation, if you rotate the orientation, it becomes a little bit easier. G of y, so for graphing something like x equals 3 minus y squared, you think of graphing y equals 3 minus x squared. Okay, so here's the graph of x squared. Negative x squared just rotates it about the x-axis, and then the 3 will shift it up 1, 2, 3 places. Okay. But we are in the other orientation, so that picture, you know, with Riemann person going up the flagpole like this, that picture is going to be like this. And then the other function, the y plus 1, in this orientation, to get a positive slope, you think about the Riemann man where he's sitting, where Riemann person where they're sitting. So anyways, a y plus 1 positive up 1 over 1, it'll be like that. Okay. So a positive slope in this other orientation looks like a line that has positive slope in the end. So look, the slope is positive here, right? And that was for this Riemann person. But it's the same if you have this other orientation, right? And this orientation, as Riemann man goes in this direction, the slope of the line is positive. Okay. For this orientation, the slope of the line is negative. Okay. And then for this orientation, where Riemann person is going up the flagpole, whoops, I just drew a positive slope. This would be the negative slope. So you can see in either orientation, the slope is kind of, the picture, the end picture is kind of the same. I hope that makes some sense. But anyways, that's our picture. And so the top this time is the parabola, and the bottom is the line, the equation of the line. Okay, so the top, or the curve to the right, is the 3 minus y squared, and then the bottom curve, y plus 1. Okay, last but not least, we need to tell the Riemann person where to run, going from where to where. So we'll have 3 minus y squared equals y plus 1. I'm going to move the y squared to the other side, so I'll have y squared, and then plus y, and then minusing 3 on both sides, get a minus 2 factor. And I believe we get negative 2 and 1, so that will be the limits on our integral. And then evaluate. 3 minus y squared minus y minus 1 will give you 2 minus, let's put the y first, and then minus y squared dy. So simplify before you integrate, okay? And then this will be 2y minus y squared over 2 minus y cubed over 3. Evaluate from negative 2 to 1. And we get 2 minus 4, rather, negative 4. No, sorry, it's 2. I am right. Ugh. 2 times 1 is 2. 2 minus 1/2 minus 1/3 minus, plugging in negative 2 now, negative 4. Minus 4 over 2 is 2. Then it'll be a plus 8/3. Looks like the same answer as before. Okay. 2 plus 4 plus 2 is 8. And then there's a negative 9/3 when all is said and done. That'll be minus 3, minus 1/2. So yeah, 9/2. Okay. So you know, expect 1 of each orientation on the test, and then we finally get into 7.2 where we're dealing with disk or washer. So the formulas for these, they'll have you'll be looking for a radius function. So if it's disk, it'll be pi r squared. If it's washer, so this is disk, and then if it's washer, you need a big radius and a small radius. Okay. Washer. Okay. The base of the rectangle tells you the variable you're working with, and for disk and washer, the rectangles are always perpendicular to the axis of rotation. Okay, so rectangle base tells you if it's in terms of x or in terms of y. In other words, what is your input variable? And then the rectangle is perpendicular to the axis of rotation. And again, I'm only going to put x-axis and y-axis problems. I'm not going to be doing shifted axes. There's just not enough time for the summer classes to get carried away. Okay, so let's look at number 11. And we're given sort of our function is square root x, and the region is enclosed by these other two curves, and we're rotating about the x-axis. Okay, so first sketch a picture. Okay, make a sketch. So the square root of y function is like a sideways facing parabola, just 1/2 of it. Y equals 0 is the x-axis, and then x equals 3 is a vertical line at 3. So the region we're rotating is this region, and we're going about the x-axis. The rectangles are perpendicular to the axis of rotation, so there you go. And so it's in terms of x, and Riemann-Person is going in this direction. It's a disk, so we need a formula for the radius in terms of x. So the radius is just going to be the height of that rectangle. It should be square root x. And so we have pi times r squared dx. And Riemann-Person is running from 0 to 3. Okay, and then we just evaluate that, and that will be our answer. Square root squared gets rid of the square root. This will be pi x squared over 2 from 0 to 3, so that will be 9 pi over 2. Let's look at the next guy, number 12. The region is a little bit more complicated. We have two parabolas. The first parabola is easy to draw. It's just kind of the standard form. The second one, though, you may need to get the vertex for it. So the x-coordinate of the vertex is negative b all over 2a. You can memorize this. I mean, you could try to shoot from the hip with a graph in your calculator if you need to, but I advise you to literally, if you have to, get the x and y coordinates by hand. So anyways, you have negative b over 2a. So that would be negative 4 all over 2 times negative 1. Negative by negative is positive. 4 by 2 is 2. And then back sub to get the other coordinate. That will be 8 minus 4, which is 4. And then if you need the intercepts, just set it equal to 0. I mean, you get an idea with your graph, but it's much safer to do this by hand, okay? Especially if people's lives depend on it. You don't want to just always depend on the computer, but as the computers get more complicated, it gets a lot harder to check by hand, I guess. But 2, 3, 4. There's our intercepts. At 2, I got 1, 2, 3, 4. So our first parabola looks like this. And then the y equals x squared. Let's figure out where that intersects with the other parabola by setting them equal. Let's add the x squared to the other side, subtract the 4x, set it equal to 0. Factor out 2x, so we get x minus 2. So they're hitting at x equals 0, and then at x equals 2. Okay, so the first parabola is going like that, and then the second parabola is going like this. And then the region we're working with is this region, and we're rotating it about what? So going back to the question, it says x-axis. Okay, okay, great. So the rectangle, again, is perpendicular to the axis of rotation for disk and washer. So there's a rectangle. It'll be in terms of x, because the base of the rectangle can be projected onto the x-axis. Riemann person is in this orientation because we're in terms of x. We need a formula for the big radius and then the little radius. Okay, so big radius distance is the distance to the top of the rectangle, and that is given by the upside down parabola, which is the 4x minus x squared. And then the little radius is the distance to the bottom of the rectangle, and that's given by the y equals x squared. Okay, so it'll be this x squared. Okay, finally then we can evaluate this by doing the integral of the two radii, the difference of the radii squared. So it would be the top one, the big one first, squared, and then minus the small one squared. And then foiling, some foiling, and the Riemann person is going from 0 to 2. So doing a bit of foiling, then we get 16x squared minus 8x to the third plus x to the fourth minus x to the fourth. Simplify before you integrate. And then this guy is going to be pi times the integral of 16x squared minus 8x cubed. And then we could power rule that guy. Eight x to the 4 over 2, let's simplify that. That'll just be 8x to the 4th over 4 is going to be 2x to the 4th. And then we have pi times, let's see, 16 times 8 is 128 over 3, minus 2 times 16 is 32. Find a common denominator, subtract them together. And that's going to be 32 thirds pi. Okay, great. From there, we have then 7.3. So the formula you need to memorize there is the shell method formula, and you're always going after a radius and a height function. So the integral is 2 pi integral radius function times height function, and then whatever your variable is. And for these problems, that radius function is always just going to be x or y. So if it's a y-axis rotation, it'll be y. If it's an x-axis rotation, it'll be x. The base of the rectangle, again, tells you what your input variable is. And then the shell rectangles are parallel to the axis of rotation. Okay, so for washer and disk, all the rectangles are perpendicular to the axis of rotation. For the shell method, shells are parallels. Okay, so rectangles are parallel to the axis of rotation. Okay, so problem 13, sort of the same. And I'll tell you which method I want you to use, shell or is it disk or washer. And just read the directions. Please don't use your own method. I need to verify that you've learned all the material. Okay, so part of my job is just making sure you reach all the goals of the class. Okay. So anyways, we got y is square root x, then y is 0, then x is 4, and we want to do a y-axis rotate. So first, give me a sketch. So y equals square root x again is this half parabola. X equals 4 is a vertical line out here, and y equals 0 is the x-axis. So the region we're rotating is this red region. We're going about the y-axis this time, and the shells are parallel. Okay, so the shell rectangle will be parallel to that axis of rotation. The base is on the x-axis, so our formulas need to be in terms of x. For x and y-axis rotations, rho of x is x, rho of y is y, so here is just x. And then the height is the height of the rectangle. So in this case, that's just given by the function square root x. So Riemann person is running across the x-axis again from 0 to x equals 4. And then we have 2 pi rho of x times h of x dx. Okay. To integrate that guy, you multiply out the x and the x to the 1/2. That will give you x to the 1 plus 1/2 is 3/2 dx. So this will be 2 pi x to the 3/2 plus 2/2 is 5/2 times 2/5. And of course we need to be able to evaluate this thing. Making sure I got it right. Did I do it right? So, oh, there's a mistake in my notes. I just found a mistake in my notes. That's what I did wrong. Uno momento. I never integrated, so 5. Oh, gosh, let me pause the video a sec. Hold on. All right, so this would be then 4 pi over 5, where Riemann person is going from 0 to 4. So we'll plug in 4, you get 4 to the 5/2 minus plug in 0, 0 to the 5/2. 0 to the 5/2 is just 0. 4 to the 5/2, that's 2 to the 5th, which is 32. 2 times 2 is 4, 18, 16, 32. And then 4 times 32, I believe, is 128. Pi over 5. All right. Next, we got another shell problem, number 14. Again, draw the area first. So the region given by these curves, and then rotate it about x-axis this time. So draw it. Y equals x is just the diagonal through the origin. Y equals 0 is the x-axis. X equals 2 is a vertical line at 2. So that's this region we care about. I want to do an x-axis rotation. And for shells, the rectangles are parallel. And then the base of this rectangle is projected onto the y-axis, so everything should be in terms of y. So I need a radius function, rho of y. It's automatically just y in these cases. And then a height function for that red rectangle. Okay. So the red rectangle, its height is given by the distance to the top minus its distance to the bottom, right? So the distance to the top of that rectangle is constant, it's just 2. And then we subtract away the distance to the bottom, which is given by this formula, but we need it in terms of y, right? The Riemann person is going up the y-axis. So all you got to do is flip-flop the equation, the sides. So instead of y equals x, x equals y. So the height from the bottom, from the y-axis to the bottom of the rectangle for any particular y value is just given by y. So it'll be 2 minus y for the height function, and then we go to our integral, so that would be 2 pi integral y times 2 minus y dy. And we are running from 0 to 2 on the y-axis. Basically, to get the y-coordinate of that point, you're just setting x equals 2 into the formula. So you know the x location is 2, and then just plug 2 into this formula, so y would equal 2. Okay, so Riemann person is going from 0 up to 2. Okay, then you integrate, so 2 pi integral 2y minus y squared dy, and then power rule on it, 2 pi times, this will be 2y squared over 2 is y squared minus y cubed over 3 from 0 to 2. I'll lay 2 pi times 4 minus 8/3 minus 0 minus 0, so just 4 minus 8/3. 4 minus 8/3 is 12/3 minus 8/3, which is 4/3, and then that'll be 8 pi over 3. Okay. So couple shell problems. Then the final type of problem we need for our test is the arc length formula from 7.4. Again, there's no 7.5 on the test. But anyways, the arc length formula, S is equal to the integral of the square root of 1 plus f prime of x squared dx from whatever a to b. Okie dokie. So, problem 15. We have y equals 2/3 x to the 3/2 plus 1 going from 0 to 1. And I get its derivative, y prime. It's 2/3 power rule, bring down the 3/2. X to the 3/2 minus 1 is x to the 1/2. Derivative of 1 is 0. Squaring this thing before I put it into the integral, of course, simplifying a little bit. You got x to the 1/2 squared, which, believe it or not, is just x. So our integral, s, will be the integral from 0 to 1, square root 1 plus x to the 1/2 squared, which we just found to be x. Then this thing, you could do a u sub for 1 plus x if you wish. So du will just be dx. So the integral of u to the 1/2 du, power rule, back sub, evaluate, so 2/3 times, plug in 1, so you get 1 plus 1 to the 3/2, and then minus, plug in 0, you just get 1 plus 0, which is 1 to the 3/2, 1 to the 3/2 is 1. If you wish, you can just leave your answer in that form. Final problem I put on this pretest, number 16, y equals ln of sine x. And, okay, so we need the derivative. So y prime is going to be 1 over the guts times the derivative of the guts. Cosine over sine is cotangent. So you should know your basic trig identities. And then we dump that into our arc length formula, so it'd be the integral of the square root of 1 plus cotan squared x dx. 1 plus cotan squared. Okay, so we have our fundamental identity, sine squared plus cosine squared equals 1. If you divide it all by sine squared, you get 1 plus cotan squared equals cosecant squared. So it seems I can replace the 1 plus cotan squared with cosecant squared. So the square root of cosecant squared x dx, which will work out nice, right? Because the square root of something squared, you know, those will cancel. So you just get cosecant x dx. And then the hint I give tells you that that's equal to the ln of the absolute value of cosecant x plus cotan x, evaluated from pi over 4. That's given in the problem as well, to 3 pi over 4. Where is 3 pi over 4? That's in the second quadrant. So sine is negative, or sine is positive, cosine is negative in that quadrant. Okay. So this will equal negative ln cosecant of 3 pi over 4 is root 2. Cotan of 3 pi over 4 is negative 1. And then we go minus negative ln absolute value. Now we evaluate pi over 4, so cosecant of pi over 4 is root 2. And then cotan of pi over 4 is just 1. Okay. And then we could get an approximation or rewrite negative ln absolute value root 2 minus 1 plus ln absolute value root 2 plus 1. Okay, but that answer right there is fine as well. Okay, so that gives you a pretty good idea of the test. So I'll be taking problems similar to these from the question pool. Every once in a while, I'll take the exact same question. I'll just change the numbers. And then also, I'm allowed to take some problems from the book, just to keep everybody honest, if I wish to. So, as usual, I hope this helps, and I'll see you next time.